So the here this is the ammonia converter where ammonia reacts with oxygen, produces NO. This is highly exothermic reaction and it is a irreversible reaction. So this can be operated at high temperature. So, but one problem is that for the nitric oxide to NO2 should be carried out between 400 to 500 Kelvin temperature, whereas the gases leaving this reactor will be at more than 1200 Kelvin. So this intermediate cooling is required. So the boiler feed water is utilized to generate steam here. Again, boiler feed water is utilized to generate steam here. Then we have the condenser to cool the temperature further down and also to condense the nitric acid vapors which is formed during this reaction, during this while it is traveling from reactor to condensers. So the weak nitric acid and nitrogen dioxide, that gas is introduced into this absorption column and air is introduced from the bottom. So the air and nitrogen dioxide reacts and nitric oxide and air and oxygen reacts here and produces NO2, and NO2 and water reacts in the same column and produces HNO3. So that way we are getting nitric acid here of 62 to 52 to 65.8%. Now here, we can never say the reaction is 100% will happen. The oxidation of nitric acid 100% will happen. Some unreacted NOx, that could be NO or NO2 or any other forms of the nitric oxide, those will come out. We cannot directly leave them to atmosphere. We cannot simply dump into atmosphere because these NOx gases are highly toxic and hazardous to the air pollution. So before we leave into atmosphere, that has to be converted to some other suitable form. So what I'm saying here is whatever unreacted NOx gases in this from this absorption column, we cannot directly went into atmosphere because these are all hazardous, very toxic. So I'm putting the general form of NOx because it could be NO or it could be NO2 or it could be any other form of nitrogen that is formed. Nitric oxide is formed during this heating in the process overall. So instead of leaving into the atmosphere, that enters into the catalytic converter. NOx converter. So this is the catalytic NOx converter. We see similar type of converters in our bikes. Suppose if we use two-wheelers, we use air as an oxidizing agent of the fuel in the combustion engine of the two-wheeler or four-wheeler. Now during that oxidation, this nitrogen may react with or often reacts with oxygen and form some NOx wastes. So that we cannot directly vent into. That is where we have the exhaust pipe in our two-wheeler or four-wheeler exhaust pipe. This is the typical catalytic converter. If you observe any time inside, this is a converter. So this converter basically converts the NOx components into the more stable and unharmful components. So whenever this exhaust pipe is not working, you will see the dangerous smoke comes. The dangerous smoke comes from the two-wheeler or four-wheeler. If this catalytic converter doesn't work, because often we have to reactivate it. So if they don't do reactivation, it will emit a lot of toxic pollutant. That's why nowadays government regulations, they put in force that every vehicle every 6 months they have to do this, they have to see this testing, although nobody cares. But because this converter tend to get deactivated with time it needs reactivation. So for that reason, whether everything is going okay or not, they have these measurements like testing of emissions from any vehicle for every 6 months. We need to get a certificate, like what is the concentration of exhaust which is coming out. So similar converter is used even here, even in this nitric acid plant, even in this nitric acid plant. So how this converter works, just few more details which you will understand here. This NOx abatement or NOx reduction, this NOx gases reduction, how do we do? So this is a selective catalytic reduction. There is a selective catalytic reduction process is used, whether it could be NO or NO2, whatever form of the NOx, whether it is nitrogen oxide, nitric oxide or nitrogen dioxide, whatever it is, it reacts with ammonia and oxygen. If you have nitric oxide or nitrogen dioxide gases, reacts with ammonia and oxygen and produces N2, produces N2, nitrogen. Nitrogen is more stable and unharmful product. Nitrogen is stable and unharmful product. That is anyway there in the air. So this NOx gases, unreacted NOx gases or unconverted NOx gases from the reactor or absorption tower, instead of directly venting into atmosphere, they will convert this converter. Then the converter, this NOx gases reacts with ammonia and oxygen and produces nitrogen. Now, however, this reaction needs to be performed on this catalyst. This reactor, these reactions needs to be performed on this catalyst. So GLites or vanadium V2O5, vanadium pentoxide V2O5 supported on titanium dioxide. Either this catalyst or this catalyst can be used. Now for this type of reactions, because it also liberates a lot of heat, they prefer to use this is irreversible short residence time reactors. This is reversible and short residence time reactors. You don't need longer residence time for the reaction to happen because these are very quick reactions and irreversible reactions. So for such type of reactions, they use called monolith reactors. They use called monolith reactors. Mono refers to single. Monolith means single coated reactor. So it is like you take a cylinder, you take a cylindrical geolites or whatever, then they make into uh, small channels, cylindrical channels, small cylindrical channels, like it's a continuous simple channels. So this surface is coated with either geolites or V2O5 support material, and this is coated with geolites on this surface. So like see, you can see like a stride pore. You can see a stride pore. So you can see catalyst wash coat, that refers to the active material which is coated on the surface. So this is a typical monolith reactor looks like. If you ever open these exhaust gases or exhaust in your two-wheeler in the current vehicles, you will see these type of uh, reactors. So what happens is that through this channel, the gases can easily flow, and since the surface is coated with the catalyst particles, the reaction can happen. And anyway, this is a quick reaction, so it doesn't need longer residence times, very short residence times. It just need of the few seconds needs to be present on the catalyst surface. Then this reaction happens. Since this liberates a lot of heat, that's why the exhaust in the two wheelers very hot. By chance, if you place leg, then you will get simply skin burn. Immediately, skin burn will happen because of this. Normally, the exhaust gases from the internal combustion is already hot, And further to this catalytic conversion also will liberate a lot of heat. So that's why the exhaust pipe is very hot in any vehicles. So here the NOx gases, unreacted NOx gases are coming out, and see this is coming out. So here that gases will be cooled down. That gases will be cooled down. Then it will be passed. This the gases are entering here. This is the catalytic monolith reactor, and here ammonia is introduced. And anyway, the oxygen is coming. The oxygen is coming from this because we already introduced air here. We already introduced air here to this absorption column. So air is there, NOx gas is there. So if we introduce ammonia here, these reactions will happen. These reactions will happen, and after that you will have only nitrogen and water vapor. So we can directly vent it into atmosphere. This is the typical monolith reactors looks like this. This is the typical monolith reactors looks like this. So you can see a single module. This is the single module. Like this is one module. Like this is whole reactor, and this is a perfect structured packing example. This is the typical structured packing. Often we see random packing, like packed bed distillation column or packed bed absorption column or packed bed reactor. But often we will see random packed bed. All the catalyst particles or packaging, the packing materials in distillation column or absorption column randomly dumped. But these monolith reactors are structured packing, like the mesh type of reactors which I showed in the NOx ammonia conversion. Ammonia conversion, that is also an example for structured packing reactor, and monolith reactors also structured packing reactor. So these monolith reactors like modules are very well structured manner. They place it here, and here see this is the module, and inside the module you will have a catalyst, and we will have the catalyst layers are coated. That is zeolites are coated in the inner surface. Zeolites are coated in the inner surface. So these ammonia gases and the whatever NOx gases are sent inside along with oxygen. NOx gases coming from the absorption column and oxygen coming from absorption column are sent inside. Sorry, O2. O2. So both goes inside, ammonia comes here, and up on the catalyst surface, this conversion of NOx gases to nitrogen will take place. So the outlet gases will predominantly contain nitrogen and water vapor. And this is a quick reaction. Often we can achieve using this monolith reactors very high conversion rate. So very little amount of NOx gas. NOx gas still be there, but the concentration will be very low upon passing through this monolith reactor. So this is all about nitric acid production flow sheet. If you have any questions, kindly let me know before I move on to the next topic. As I could understand that very little amount of information is going to your, I don't know, your understanding. I don't know what is the reason, because simple questions I asked, no one could answer it. Maybe you don't want to answer it or don't want to unmute it. For whatever reason, I'm going to ask such questions in the exam. All questions will be in the reasoning based. So even if you're not paid attention, please, I want you to pay attention, because these are all important factors, important information for a typical process engineer. So I'm also going to ask such questions. So like whatever questions I asked just now. So please, even if you don't answer to me, no problem, but at least you should answer in the exam. Because if you don't answer it, I will be feel a little sad that none of you are understanding. So today we will talk about another fertilizer. That is, in India we produce two fertilizers. Okay. Before I move on, any questions from the nitric acid? Nitric acid. production process. Okay, so no questions. Probably you're all in, I don't know. I hope you're in a good mood. I hope my screen is visible. If you don't want to answer, just message me that yes, we're able to see my screen. Can anyone message me that you're able to see my screen? Or you can unmute and say also. Okay, thank you, Ayush. I hope you're all not angry with me. So, yeah, so no questions. Then we'll move on to the next topic. In India, we produce two fertilizers predominantly. One is urea, one is urea, another one is DAP, diammonium phosphate. Diammonium phosphate. So, what is the difference between urea and diammonium phosphate? Can anyone tell me what is the difference between urea fertilizer and DAP fertilizer? Which crops, which area of the fields needs urea and which area of the fields needs diammonium phosphate fertilizer? Or randomly we can put any fertilizer whatever we want, like the current farmers are doing, unfortunately. And many IIT graduates started their startups in fertilizers, crops, and all those things. Even the government yesterday in the budget, they're also announcing this technology for the farming. So at least you will show some interest, I thought. Which area or which fields needs urea and which fields needs diammonium phosphate fertilizer? Come on, students. Please answer some question. Or we can put anywhere whatever we want. Okay, let me ask this question. What are the three important elements required for the fertilizer?
NKP, nitrogen, phosphorus, and
Correct. So in the urea, which element is there predominantly?
nitrogen.
Nitrogen. So only nitrogen. Urea can only give the nitrogen. Whereas diammonium phosphate, ammonium has nitrogen and phosphate has phosphorus. Thank you. I just noted. Rushi Girish, RS for Rushi Girish. Thank you. At least you could uh, give me some answer which at least give me a little bit of satisfaction. At least that somebody is unmuted. That I'm happy with that. So urea has nitrogen only fertilizer. If a field requires only nitrogen, it has sufficient amount of P and K, only deficiency nitrogen, we will put urea fertilizer. But if the fields are in deficiency of nitrogen and phosphorus both, then they have to apply this diammonium phosphate fertilizer. So that is how we decide. And There is called complex fertilizers. So if you add, this is N is there, P is there. This is called complex fertilizer where they include potassium also. Where they include potassium also. So I will also talk about that so that I can completely finish off this fertilizers. Here I'm not only focusing on fertilizers, I'm also focusing on important bulk chemicals as you have seen, ammonia production, nitric acid production. So those I'm covering both parallelly, important for chemicals and important components, fertilizers. So today we will talk about, or rest of the today's session will be focused on production of diammonium phosphate. But this diammonium phosphate in the production requires phosphoric acid. The diammonium phosphate production required phosphoric acid. So we will also see how they make phosphoric acid. So just like urea, it is only nitrogen-based fertilizer. There are phosphorus-based fertilizers, only phosphorus-based fertilizers. So these three are the only phosphorus-based fertilizers, like phosphate rock, superphosphate, triple superphosphate. That is only phosphorus-based, P-based fertilizer. Urea is only N-based fertilizer. Phosphate rock, superphosphate, triple superphosphate is only phosphorus-based fertilizer. If you want nitrogen and phosphorus both, we have to use DAP, diammonium phosphate. If you want nitrogen, phosphorus, and potassium, all the three, then we have to use the complex fertilizer. So that is the overall answer to this fertilizer. So although I'm leading, the main lead is fertilizer, so far in the discussions, I am covering many other important things like ammonia production, phosphoric acid production, which we'll cover, and nitric acid production. So I have covered important acids also. I'm also covering the fertilizers also. So phosphoric acid production, because phosphoric acid is the raw material, one of the important raw material required for the production of diammonium phosphate. So we'll start with phosphoric acid production. So this is the phosphate rock which is available naturally. The phosphate rock is available naturally. Ca3PO4 twice. Often this phosphate rock has the impurities like silicons and fluorides. Often this phosphate rock has the impurities like SIF. These two based impurities will be there. So depends on the place to place. This impurities vary, and this based on these impurities, the purity of the phosphate rock also varies. Based on these impurities, the purity of the phosphate rock also varies. So there are two methods used in the phosphoric acid production. One is wet chemical method, another one is thermal method. One is wet chemical method, another one is thermal method. If the purity, if the purity of the phosphate rock, if the purity of the phosphate rock is lower than 30%, if the purity of the phosphate rock is between 26% to 30%, then this method is more preferable. This method is more preferable. Like I said, phosphate rock predominant component is Ca3PO4 twice, but along with this, their impurities will be there. Silica and fluorides impurities will be there. Now, it depends upon these impurities, the purity of rock varies. If the purity of the rock is low, if the purity of the rock is low, that is between 26 to 30%, then we use wet chemical method. If the purity of the rock is higher, if the purity of the rock is higher, then we use the thermal method. Thermal method is more economical. Of course, either way we can use both methods, but in terms of more economical way, If we have the phosphate rock purity is higher, then we use thermal method. If the phosphate rock is purity is lower, then we use the wet chemical method. Now, so in the wet chemical method, this phosphate rock Ca3PO4 twice reacts with sulfuric acid. Reacts with sulfuric acid. Sulfuric acid production. There is also an important chemical, sulfuric acid. And Dr. Bhaskar, when he starts his portion, after I finish this topic, he will explain the sulfuric acid production process. So you will get to know how to produce sulfuric acid, because this is very, very important acid used in almost all industries. So Dr. Bhaskar will discuss the sulfuric acid production. So this phosphate rock reacts with sulfuric acid and water and produces H3PO4. H3PO4. This is called phosphoric acid. H3PO4 is phosphoric acid, and also produces CaSO4 2H2O. CaSO4 2H2O dihydrate, and this is also known as gypsum. This is also known as gypsum. So phosphate rock reacts with sulfuric acid and produces H3PO4 and CaSO4 2H2O, calcium sulfate dihydrate, and this is also known as gypsum. So this is in the wet chemical method. Whereas in the thermal method, this phosphate rock is heated to very high temperature. The phosphate rock is heated to high temperature, and from this phosphate rock, the phosphorus liberates into vapors. The phosphorus liberates into vapors. P4 phosphorus liberates. Phosphorus vapors are liberated. So that is taken as P4. That phosphorus oxidizes, reacts with oxygen and produces P2O5. That P2O4 reacts with water and produces phosphoric acid. So these are the important reactions, are the key reactions in wet chemical method and thermal method in the phosphoric acid production. I'm sure you all know these reactions when you were, even I think you will learn in 10 plus 2 itself. These are the not new reactions to you. These are very, very common reactions. Now, if you wanted high purity phosphoric acid, you will get, you will obtain in the thermal method. You will obtain in the thermal method. If you wanted highly concentrated acid, highly concentrated acid, then we use thermal method. If you want low concentrated acid, low purity acid, we use the wet chemical method. Now, like when you want to make pharmaceuticals, we need high concentrated and highly pure phosphoric acid, and detergents production we need. So for those processes, thermal method is used. For fertilizers, we use wet chemical method. So even modern industries, although predominantly running based on wet chemical method, still there are industries which are using the thermal method. So I will talk about both methods. So what is phosphate rock or what it contains? Yeah. The phosphate rock, typical phosphate rock formula is Ca10PO46 N2X2. So this X could be anything. It could be fluoride, hydroxyl, or chlorine ions. It could be anything. Depends upon the impurities present in that one. So this can be expressed in this phosphate rock formula can be expressed as typically this form: Ca3PO4 twice and CaX2. So these ions, this X could be fluoride ions like CaF2 or CaOH twice or CaCl2. It could be anything. Now, apart from this, It can also have the sand, silicon dioxide impurities also present, and clay also present along with this phosphate rock. And in addition to this, very, very small trace quantity of impurities, that is carbonates, will also be there. The carbonates also will be there. The carbonates of sodium and magnesium also be there. So uh, predominant impurities are could be fluoride, hydroxyl, or chlorine combined with calcium, or it could have sand and clay. These are the predominant. Very minute impurities like carbonates of sodium and magnesium also will be there. The purity of rock, the purity of rock and H3V4 usually expressed in terms of P2O5. The purity of rock usually expressed in terms of P2O5. So rock from mines can vary from the phosphate rock mines. The purity of the phosphate rock mines can vary from 14 to 35% of P2O5. If you take any phosphate rock and the purity is expressed in terms of P2O5, the any rock, whatever available in the across the globe, the purity varied from 14 to 35%. 14 to 35%. So here, an important thing, please note here that if the purity is above 30% P2O5, if the purity is above 30% P2O5, that can be directly used for the phosphoric acid production. That can be directly used for the phosphoric acid production. It will be economically acceptable even for the reactors and even for the processing conditions. If P2O5 content is less than, if P2O5 content is less than 30%, then beneficiation of rock will be done. Beneficiation refers to removal of impurities. Beneficiation refers to the removal of impurities present in the rock. If P2O5 content is less than 30%, beneficiation of rock will be done to enhance the P2O5 content. To enhance the P2O5 content. To enhance the P2O5 content. So what is beneficiation? Beneficiation refers to removal of worthless minerals or impurities. Removal of worthless minerals or impurities. So we need to remove either carbonates, or we need to remove the separate the clay, or we need to remove the separate the sand, or we need to separate. Often they try to reduce this sand, clay, and carbonates to enhance the purity of the phosphate rock. To enhance the purity of the phosphate rock. So this slide, I am basically talking about three important points. That is, what is the phosphate rock? Phosphate rock contains impurities, and the phosphate rock purity is expressed in terms of P2O5. Typical phosphate rock has 14 to 35% of P2O5 purity. If phosphate rock has above 30% of P2O5 purity, that can be directly used for the phosphoric acid production. If the purity levels is lower than 30%, then beneficiation of rock will be done. The beneficiation means removal or separation of worthless or minerals or impurities. So, like since the phosphate rock contains sand and clay, often they try to reduce the sand content and clay content to enhance this purity of the phosphate rock. So, what is the how does the how do they do this beneficiation process? So they will try to wash the rock particles, big rock particles, to separate any sticky clay and sand. So they have the phosphate rocks. While during the mining process, you will get big rocks. Those big rocks are washed to separate any sticky clay or sand on the surface. Then they crush this big phosphate rock big phosphate rocks into small particles, into small particles. So for the reducing the particle size from bigger to smaller, we use crushing and grinding. We use crushing and grinding. So typical crushing and grinding, what you learned in mechanical operation course will be used. They reduce from almost like a big rocks to particles smaller than 200 mesh size. The particles smaller than 200 mesh size. I'm sure you learned in the sieving process what is the 200 mesh and what is the lower than 200 mesh and higher than 200 mesh. I'm sure you know it. So the particles lower than 200 mesh size will be, since here you can see, since here two solid particles are joined together. Two solid particles are joined together, like I showed here, Ca3PO4 twice and CaX2. Two are different elements are joined together. So whenever you have the same materials in the presence of solid form, in earlier unit operations I discussed, either we can use leaching or we can use flotation processes. So flotation is simple process, and so froth flotation, if you take these particles and put in this water and if you do the froth flotation, then all these impurities tend to come outside. All the impurities tend to come outside. So that way they will separate these impurities from the phosphate rock using the flotation technique. Now whenever we have the particles in liquid medium, to separate these particles we use hydrochlone or settling chamber. Since particle size is smaller, settling chambers will not work because the particle size lower than 200 ms is very small. So they use hydrochlone to separate the particles after after the flotation. After the flotation, the phosphate rock particles are separated using this hydrochlone. Then since it has some water, they will dry it in the rotary dryers. They will dry it in the rotary dryers. Rotary dryer or kilns they will use. I will talk about the drying process in the later slides. If I miss, I will come back and I'll explain here how do they dry these wet particles in industrial scale. Now, a quick after beneficiation. After beneficiation, if the purity is lower, we need beneficiation. If purity is higher, we don't need beneficiation. That I already mentioned in the earlier. So let's say the beneficiated phosphate rock is there. That is, purity is higher than 30% is there. If you want to use, if a fields, like if a fields needs very small amounts of phosphorus, then the you can directly apply this phosphate rock. You can directly apply this phosphate rock as a fertilizer. So they will grind it. They will directly apply as a fertilizer. Direct application of the rock. But if you need more purity, phosphorus fertilizer, then we need single superphosphate or triple superphosphate fertilizer. So how do you produce single superphosphate? The phosphate rock reacts with sulfuric acid, reacts with sulfuric acid. Now one thing important here, partial acidulation. Partial acidulation. So we will supply limited quantity of sulfuric acid. limited quantity of sulfuric acid, so that we will avoid this dihydride formation. We will avoid this dihydride formation. So only this phosphate rock is converted to Ca CaH2PO4 twice dot H2O, and this is called single superphosphate. This is called single superphosphate. So if you use very diluted acid, if you use very diluted sulfuric acid, if you take very diluted sulfuric acid, mixes with phosphate rock, what you will get is single superphosphate. You will get is single superphosphate. So the concentration of P2O5, the concentration of phosphorus is in the single superphosphate is higher than the phosphate rock itself. Phosphate rock itself. Now, if you do reaction with phosphoric acid, H2 phosphoric acid, I think I have written something wrong. Phosphoric acid here, you will get triple superphosphate. So you take the phosphate rock, and if you react with sulfuric acid, you will get the single superphosphate. If you take the phosphate rock and if you react with phosphoric acid, you will get the triple superphosphate. And again, if you take phosphate rock and react with sulfuric acid, you will get the phosphoric acid. What is the difference between full acetylation and partial acetylation? Here we treat with very diluted sulfuric acid, and here we treat with highly concentrated sulfuric acid. That is the only difference. If you treat the phosphate rock with a dilute sulfuric acid, then you get single superphosphate. If you react with highly concentrated acid, then we get the phosphoric acid, which I already showed in the previous reaction. Like here, phosphate rock reacts with sulfuric acid and produces the phosphoric acid. So apart from this, if you do the calcination, if you do the calcination, then we get defluorinated rock. If you want to liberate this fluorine, fluorines present as impurities, we will have to do the calcination. We will have to do the calcination. If you want to separate the calcium, aluminum, magnesium phosphates, then we have to do the fusion. We have to do the fusion reaction. We have to do the fusion reaction. If you do the electric reduction, that is heating with help of these electrodes, electric reduction, you get the white phosphorus. You will get the white phosphorus. So either you can use to use as fertilizer, we can directly use as fertilizer, or we can use single superphosphate as fertilizer, or we can use triple superphosphate as fertilizer. We can also use phosphate rock to produce phosphoric acid. Apart from this, we can also use to produce phosphorus, white phosphorus, because this pure phosphorus is required in the, or also utilized in the, what is called uh, any, it also uses gunpowder. It is also used as a gunpowder, like the exact name where for the blasting and other applications, they use this white phosphorus. So for that also we can use this electric reduction process. So these are all the rock phosphate end products. I just summarized all the process into a single slide. All the process into a single slide. Now we'll move on to this phosphoric acid production. I already showed you this reaction earlier. The phosphate rock reacts with sulfuric acid and water and produces H3PO4 and gypsum. I don't know what happened to my animations. All are coming at once. So this is a non-catalytic irreversible reaction. This is a non-catalytic irreversible reaction. Phosphate rock, that is rock particles, reacts with sulfuric acid and water, produces H3PO4 and gypsum. and this doesn't need any catalyst and doesn't need it is a irreversible reaction, and it is operated at atmospheric conditions. It is operated atmospheric conditions. What reactor should we use? CSTR or PFR? Students, what reactor shall we prefer to use? Again, the scenario is rock particles has to be reacted with acid. That is the scenario. Which reactor do you think we should use? CSTR or PFR?
Like, yes, we'll use PFR because CSTR requires continuous flow.
True. So CSTR requires continuous flow. Now, do you think mixing is required or not for this one? If you don't mix, what will happen to the particles? In the PFR, suppose if you don't mix, what will happen to the particles? Will they settle or not?
Yes, the rocks might settle.
Yeah, since rock particles are not in a nanoscale, they will settle. So the mixing is required, no? Although mixing is energy intensive compared to PFR, but mixing is imperative, right?
Yes, sir.
So that's why we use CSTR in this case rather than the PFR. Thank you. So we use CSTR in this case than the PFR because the particles needs to be suspended. The particles should not be allowed to settle. If they settle, the reaction will not happen. So, or it will be very low yields. So we use CSTR in this case. So here, this is the typical phosphoric acid production, and this part I have taken from this Dryden's book. So far, what I've discussed that is from the other book. So this ground phosphate rock particles means whatever phosphate rock is there, that is ground means crushed and grinded into small particles lower than 200 mesh size is fed into this reactor. This is the weighing feeder so that the exact quantity of the particles are being introduced into the reactor. Based on this weight, based on this weight of this particle, using this control valve, required amount of acid will be supplied. Required amount of acid will be supplied, and this is a concentrated acid. So that's why concentrated sulfuric acid is highly corrosive. That's why only required amount of acid needs to be introduced. So they will weigh the particle by using the weighing feeder. Based on this amount of particles are fed to this CSTR, this control valve is adjusted to introduced required amount of sulfuric acid. Required amount of sulfuric acid. So this is a CSTR. You can see very simple hollow cylindrical tank with a stirrer. That is simple reactor. Not at all any additional features. So this is no exothermic, no endothermic, liberates very less heat. It still liberates heat, but very less. And so we don't need any intermediate cooling and no catalyst. So simple CSTR is enough. So in this CSTR reaction happens. Now you will see that it will do in a two different like series of CSTRs. This will be done in a series of CSTRs. Now, one important thing happens in this first reaction is this in the sand. Although we try to do the beneficiation process, remove sand as much possible, but still some amount of sand will be there and fluorides will be there. This fluorides and sand can liberate a lot of vapors. That is SiFr and HF. And always the fluorides are dangerous. Always the fluorides are dangerous. So these vapors, which are all forming in the reactor, which are all forming reactors in the form of vapors, that we cannot even vent it to the atmosphere. We cannot even vent it into atmosphere. So whatever vapors form, they will send to this vacuum flash cooler. They will send to this vacuum flash cooler. They will cool it under the vacuum conditions. They will cool it under the vacuum conditions. So, so this whatever vapors which is formed, SiF or HF, this vacuum flash cooler, they will condense it into liquid, again introduce back to the reactor. Because since we cannot let these vapors to go outside, and also we cannot let them in the vapor phase for a long time, so the time to time these vapors are taken and cooled and again introduced back to reactor, so that vapors will be go in the solid form. Like later we have the gypsum formation. These SiF4 and HF will mix with gypsum, and anyway gypsum is going for the either construction or the construction purposes. So that will be stays in the gypsum solid with less chance of liberating into the atmosphere. That's where they will cool it and make this liquid, again introduce back to the CSTR. So whatever impurities present in the phosphate rock, they will tend to form this SiF4 and HF vapors. So these vapors, any fluoride vapors are highly dangerous. So even if very small quantity, we cannot introduce into the atmosphere. So those vapors are cooled and converted as a liquid, again introduced back to the reactor. Why are we introducing the reactor? So these SiF or HF tend to mix with gypsum as a byproduct which is formed, which I showed in the previous reaction, CaSO4 2H2O, and stays along with the gypsum, so that will be remain as a solid product for longer time. So if at all, why are we using the vacuum flash column? Because even if some uncooled vapors, they will be taken and mixes with the gypsum solution. They will mix with the gypsum solution and sent to the gypsum storage tank, gypsum storage place. So that way, ultimately, we don't want these vapors to go outside. Ultimately, we don't want these vapors to go outside. So, gypsum solution is passed, and whatever vapors is collected, they mix with the gypsum, and it goes outside. So after this reaction, that is phosphate rock reacts with sulfuric acid and produces the phosphoric acid and gypsum. Phosphoric acid and gypsum. Now here two things come outside. If you see reaction, two things comes outside. That is phosphoric acid and gypsum. These two are comes outside, and you know this is solid. This is solid, and this is liquid. After the reaction at the atmospheric conditions, the gypsum is in the solid form and phosphoric acid in the liquid form. So here we have all these reacts coming. So two things coming out: phosphoric acid, P acid, gypsum, phosphoric acid, and gypsum are coming. Gypsum is solid and phosphoric acid liquid. P acid, okay, phosphoric acid. This is solid, this is liquid, this is solid. So we need to separate solids from the or liquid from the solids. We need to separate the solids from the liquid. So here we're talking about solid liquid unit operation. Solid liquid unit operations. So whenever we have the solids needs to be separated from liquid, we go for the filters. This is almost like a slurry. Here is almost like a slurry. If gypsum is present as particles, then we might go for hydrochlone. We might go for hydrochlone, but this will be like a slurry. If you use the slurry form, we can never use any cyclone separators for the separation. So this is slurry form. So we prefer the filters. We prefer the filters. So of the two filters, we have plate and frame filter press, and we have the rotor drum filter. These are the two popular, although many other things are there. So in the phosphoric acid production, they prefer to have rotary drum filter because this is a continuous process. This is a continuous filter, whereas plate and frame filter process batch one. So we need to separate, clean it again, do it multiple times. And if it is highly sticky, where its cleaning is difficult in a quick way, then ultimately we have to go for the plate and frame filter press. But here the gypsum is easily removable material from the filter cloth, easily removable material from the filter cloth, and that's why we can use the continuous filtration process that is called rotary drum filtration process. So I have already explained to you. So this is the drum, rotary drum, RD, rotary drum. This drum is covered with a fine filter medium, that is a filter cloth, the covered filter cloth. So this is just filter cloth, and the gypsum and phosphoric acid slurry is sent to this bottom tank. Then the vacuum is applied from the center, and the filtrate, that is phosphoric acid, will be pulled inside, and the gypsum particle sticks on the filter cloth, and they will be removed using the doctor's knife. And so these are the gypsum particles sticking onto the surface of the filter cloth is removed, and they will go to the gypsum pond. So the gypsum solution from here and the gypsum from this Rotterdam filter will goes out for the gypsum pond. Of course, there are a lot of things to talk about gypsum, what are the utilities and all those things. And the phosphoric acid which is collected from the vacuum pipe will be sent to this because whatever the phosphoric acid come from here, this is not highly concentrated, very dilute. So here we use vacuum evaporator to concentrate it, so that way we get the concentrated acid and goes to the storage tank. Now whenever we have the vacuum, we have the vacuum generators called jet ejectors. I think I have already told you the jet ejectors. So jet ejectors are connected here to generate the vacuum in the large columns here. So that way, that way the water vapors are removed, and you will get the concentrated acid. So this is the very simple, very simple phosphoric acid production process. Very simple phosphoric acid production process. What is So maybe I'll pause it for 2 minutes because theory course continuously speaking for 50 minutes might be boring to you. So I'll just pause it. You might think if you got any questions, you can ask me. Otherwise, you can drink some water. Then I will continue the class after 2 to 3 minutes. So I'll just pause it here. You might take a short break just to refresh. Yeah. So another process to produce phosphoric acid from the phosphate rock is thermal process. Thermal process. So this is the typical reaction uh, in the thermal process. That is phosphate rock reacts with carbon and SiO2 and produces phosphorus. Here usually get white phosphorus. Then we get the other byproducts. So it's a very simple process. But whereas we need to supply a lot of heat, we need to supply a lot of heat and also instantaneously. So whenever we need very high heat and instantaneous supply if required, it's always advisable to use electric ovens. So the typical electric ovens will have these electrodes, the wires, which will generate a lot of heat. So here what we do is we need phosphate rock. What they do is, so this is the phosphate rock. So rock phosphate, raw phosphate, and carbon required. So coke, SiO2 required. So this is the gravels. This is the gravels. So all the three components are uniformly mixed. This is one solid material, this is another solid material, another solid material. All the three solid materials are uniformly mixed, introduced into this electric oven. In this electric oven, three electrodes are connected, and which is supplied to the three-phase power, and will give you the high amount of heat or high amount of power is supplied, which generates a lot of heat, here. So lot of heat here. So during that heating, this this reaction happens. This reaction happens. So this is the slag. This is the slag CO dot SiO2. This slag will be in the liquid form. That slag will be removed from this oven, and here phosphorus vapors, carbon monoxide vapors will be comes outside. The phosphorus vapors and carbon monoxide vapors will come out from this oven. Now, often along with these vapors, because we are heating very high temperature and the materials is introduced, the vapors are taken out. Often there's a very very high chance of fine particles of fine particles of coke, or fine particles of sand, or fine particles of phosphate rock might also come along with this phosphorus and carbon monoxide vapors. So whenever we have this fine particles comes out with vapors, we need to separate solid particles from the vapors. So here one of the important unit operation is electrostatic precipitator. So the fine particles of rock or coke or gravels from the phosphorus and carbon monoxide vapors are removed with help of this electrostatic precipitator. So the dust particles are removed. And the vapors, the phosphorus vapors and the carbon monoxide vapors are sent into this one. And these phosphorus vapors collected, phosphorus vapors are like phosphorus particles, like very, very fine particle. The vapors are, as soon as comes in contact with water here, they will convert into particles, and those particles are collected like a scrubbing. We have carbon monoxide and phosphorus vapors, As soon as we spray the water from the top, this phosphorus vapors convert to the phosphorus particles, whereas carbon monoxide will not change, will remain in the gaseous form, and the carbon monoxide will leave. Or the carbon monoxide goes to the next operation where they will utilize it for the different purpose. And these phosphorus particles along with water is collected and stored. This phosphorus particles, this is white phosphorus. The phosphorus which is generated here is white phosphorus. And white phosphorus is highly reactive. The white phosphorus is highly reactive. We cannot store it as gas as it is, or we cannot store it as a solid as it is. That has to be always stored under water. Why? It is highly reactive. If it comes in contact with oxygen by any chance, it immediately oxidizes and releases a lot of heat, and it is very very nasty. So white phosphorus is always not a stable one. White phosphorus is not a stable one and highly reactive. Whereas red phosphorus is highly stable, we cannot store even at the room temperature. Whereas white phosphorus cannot be stored. Here I'm talking about two things. White phosphorus and red phosphorus. White phosphorus is not stable and highly reactive. So whatever phosphorus generated from this thermal process is in white phosphorus. If you want to store white phosphorus, it has to be stored under water. Like phosphorus particles should be filled with water, stored under water. So that's why they do the scrubbing. They do the scrubbing. We have a gaseous mixture and we want to separate them. So we can use one of the process called scrubbing with liquid. So they just spray the liquid. They'll convert these phosphorus vapors into phosphorus particles, and those white phosphorus particles are submerged or stored in water so that it is safe condition. Now, if you take this white phosphorus and heat it to high temperature, that will be converted to red phosphorus. That will be converted to red phosphorus. So this simple sintering process happens. During sintering process, the crystal changes to more stable red phosphorus. Just like, if you take calcium carbonate, carbonate ions reacts with calcium ions, forms the calcium carbonate. This is called polymorphism. Some of the minerals, they will present in the different forms, different crystal forms. That's called polymorphism. Like phosphorus, calcium, magnesium, they have the polymorphism. Many biominerals, naturally available minerals, they'll always have the different morphism, different structure. So so if you take calcium carbonate, we will see veterite, aragonite, and calcite. If we take the calcium carbonate, we have the veterite, aragonite, and calcite. All are calcium carbonate only. Calcite is more stable. What we see, the calcium carbonate, what we see is the most stable calcium carbonate, that is called the calcite. But before, it will easily, whenever you make any calcium carbonate, first it will form veterite. Then it will convert to the aragonite. Then it will convert to the calcite. Just like that, as soon as you liberate the phosphorus from here, that will be the more unstable phosphorus, that is called the white phosphorus. Now, if we convert that into the red phosphorus, that is more stable, that can be stored. This is not, the reaction is same, everything is same, just the crystal arrangement upon solidifying, upon crystallization, the crystal arrangement is slightly different. And one is unstable, one is stable form. Why the nature is producing unstable form? Because only in the unstable form, the conversion to other form is easier. In the stable form, the conversion is not easier. It requires external additional energy to convert it. Like if you take calcium carbonate in the the calcium carbonate in the calcite form, you cannot dissolve in water. You cannot dissolve in any organic solvents. Even chloroform that can dissolve many of the polymers, but the calcite will not be dissolved in this chloroform. So this is more stable. But in the oceans need calcium ions, carbonate ions. So if you want to dissolve it in water, if you take veterite form, you can easily dissolve in any solvent, organic solvent, or you can easily dissolve in water also. That is the nature's beauty. Same material that can form in different forms. One form easily dissolvable, another form not at all. It's very difficult to dissolve it. So that is the beauty. Similar phenomena that's called polymorphism. So the white phosphorus particles are more unstable, but when you heat it, if you take white phosphorus and heat it to high temperature, I don't remember the exact temperature right now, but it's there in the book. So if you heat it, that will be converted to red phosphorus. What will only changes is just crystal structure, just crystal structure. During the sintering process, crystal structure slightly altered, that will form the more stable form that's called red phosphorus. Red phosphorus we can store in the normal atmospheric conditions also. So this is where we get the phosphorus, and this phosphorus reacts with oxygen and produces P2O5. This is simple oxidation. That produced P2O5 reacts with water and produces H3O4. This is very easy process. So we have phosphorus and have air sent to a combustion chamber. We have phosphorus and we have air. Both are sent to a combustion chamber. Then you get the P2O5. Then we have the, instead of using water, they will deal with the very weak acid, very weak acid, so that the recycling will be easier. So this is simple absorption column. So whenever we have the gas, and if one solvent is water, we don't need to use reactor. We can directly use an absorption tower to do this reaction. So instead of water, we circulate weak acid, very dilute acid, weak acid into this absorption tower. And here we have the P2O5 gases are coming. P2O5 gases coming, and the weak acid is coming, and as as both as both travel as both travel, this conversion of P2O5 to P2O5 reaction with water, that is absorption, takes place, and acid is produced at the intermediate streams. At the intermediate streams, the weak acid is taken, and the acid is taken and diluted with water and used as a solvent, because that enhances the absorption capacity. When if we use only water, the absorption of P2O vapor is limited. But if we use weak acid, then we can enhance the absorption rate. We can enhance the dissolution rate of this P2O vapors into this liquid solvent. That's why they're using the weak acid. So they will take the intermediate concentrated acid, dilute with water, then they will supply as a weak acid as a solvent for the absorption of P2O5. Upon absorption of P2O5 with the weak acid, this P2O4 reacts with water and forms the phosphoric acid. So that way we can get the strong phosphoric acid, and that can goes to the storage. And here during the mixing, some heat is generated. So this heat of mixing, that the generated heat is cooled before removed using this cooler before the phosphoric acid is sent to the storage tank. So this is thermal process. One is, first we produce the white phosphorus from the heating, then oxidation followed by the absorption with the weak acid. So that's about phosphoric acid production. Both wet chemical method and thermal method, both are discussed. So try to relate, although this is continuous theory, try to relate or how they're making. If you show little interest, oh, we are making this product, oh, we are using this unit operation, why are we using this unit operation? If you try to use your intuition to understand that, then you will not feel boring. But if you just say watch like another video or something, then definitely it is boring. And this is very simple and dry. I don't know, maybe if I put some live reaction something, it might be interesting, but with the current infrastructure what I have, I'm not able to carry out any reactions. So One way I can say sorry, but I request you to pay a little attention, because the subject at some point of time it is like that. I'm also thinking what best way I can improve it, but I don't know. Uh, there could be some practical demonstration or something could be helpful. These industries often doesn't available in video form to even to see in a YouTube or something. And I am not very good in animation software or something to make it very animated and make it more interesting. I hope with time in the future, as I progress, maybe I could make it more animated, more interesting to students. But at the current situation, you all have to bear with me. Please pay attention. That is only my request. Yeah. So diammonium phosphate. Here we're talking about another important fertilizer, diammonium phosphate. So we could generate phosphoric acid from the phosphate rock, and these are the three raw materials we used. We used here phosphoric acid and anhydrous ammonia, and sulfuric acid is only to for the grade adjustment. Like, if you don't want sulfuric acid is only used for the grade adjustment. I will talk about this after 2 minutes. So these are the reactions. Ammonia in the diammonium phosphate is produced from ammonia and phosphoric acid. So we already seen ammonia production process and phosphoric acid production process. So ammonia from the ammonia plant and phosphoric acid from the this phosphate wet chemical or thermal method, both comes and reacts and produces monoammonium phosphate, that is NH4H2PO4, monoammonium phosphate, MAP, monoammonium phosphate, and it liberates heat exothermic reaction. This monoammonium phosphate, NH4H2PO4, further reacts with ammonia, and produces diammonium phosphate. That is NH4 twice HPO4. Now here, monoammonium phosphate can also be used as a fertilizer. Diammonium phosphate also can also use as fertilizer. So what is the difference? Nitrogen content in monoammonium phosphate is lower, whereas nitrogen content in diammonium phosphate is higher. So based on the soil requirements, nitrogen or phosphorus content requirements, one can choose whether MAP or DAP. If we want, MAP, DAP, the nitrogen content in MAP and DAP, even if it's not sufficient, if you want to add some more nitrogen requirement, you can add excess ammonia and react with sulfuric acid, and you can produce this, and that can be combined with DAP, so that you can introduce more and more amount of nitrogen. So that is called grade adjustment. Based on the requirement of nitrogen, we can perform the side reaction if required. Otherwise, we don't need to perform. So that is how they use this diammonium phosphate reactions. Again, these are very, very simple, not very, very simple. Now here I just showed whatever I told before. I've just explained. These are the typical DAP granules, diammonium phosphate granules. Actually, I forgot to put this source. I'm sorry. This I have taken from an image I have taken from my industry website. So monoammonium phosphate contains 11% of nitrogen and 55% of phosphate in terms of the P2O5 content. So that can vary, that can slightly vary grade to grade, and depends upon the concentration of this phosphoric acid in water. Some grade can have 11%, 55%, some grades can have 10%, 50%, Some grades can have 11 to 50%. The different industries produces different grades. This all depends upon the just purity of the phosphoric acid. In the diammonium phosphate, as you see, the NH4 twice is there, so this nitrogen content is increased. Nitrogen content will be increased. So DAP will have 18% of nitrogen and 46% of P2O5. So if you want further increase in nitrogen, that is more nitrogen and less phosphate in the fertilizer required, then what we do is this grade adjustment. That is, some ammonia react with sulfuric acid and produces NH4 twice SO4. That way, the this phosphorus content can be reduced and nitrogen content can be increased. That's why they use for the sulfuric acid also in the DAP production process for the grade adjustment. This totally depends upon the requirement of the fields. So it is very simple. This is a simple neutralization reaction. You have ammonia and you have acid, then we have the salts are precipitated, solids are precipitated. This is simple neutralization reaction. So there are two things in the ammonia production. This is called pre-neutralizer. Pre-neutralizer. That is ammonia and phosphoric acid at a ratio of 0.6. In stoichiometric ratio, we need 1:1 ratio. We need 1:1 ratio. But in the instead of doing that, they do it different way. They will do the pre-neutralizer, that is ammonia with phosphoric acid at a ratio of 0.6, and balance of ammonia is added in the granulator. Rather than complete neutralization, they'll add the remaining ammonia in the granulator. Or they can also do it excess amounts of this one, then they will add phosphoric acid later. So if you take the less ratio, you will add ammonia later. If you take excess ratio, you will have to add the phosphoric acid later. Instead of me saying the reason, I want you to explore why is that they do this instead of simply neutralizing this. I want you to explore. If you don't get it, then I will be happy to answer later. But for time being, just for leaving for intuition to understand this. So again, lack of time constraint, I just copy pasted the flow sheet. Again, this slide I have taken from source. I will add the source. I'm sorry for not putting the source and presenting it without source. So H3PO4, phosphoric acid, and ammonia goes to the pure neutralizer, pre-neutralizer. This is a simple CSTR. This is a simple CSTR where nitrogen to phosphorus is at ammonia to phosphorus is at 0.6 ratio. 0.6 ratio. So H3PO4 is supplied more than ammonia. H3PO4 supplied is more than ammonia. So in this pre-neutralizer, ammonia and phosphoric acid reacts and produces monoammonium phosphate. Monoammonium phosphate. I gave a hint here. So in the pre-neutralizer, ammonia and phosphoric acid reacts and produces the MAP, monoammonium phosphate. Upon this neutralization, you will have granules like solid particles, but you will not get granules so easily. Rather, you will get a slurry kind of thing. Because as soon as you precipitate it, you will not get a very, very solid shape or required spherical particles or whatever you wanted. Like here you see, these are all in the spherical particle. But upon this neutralization, it will form solid. But the solid precipitates like a slurry. So here we have the granulators. Here we have the rotary granulators. Here we have the rotary granulators. So in this rotary granulator, since we have added less amount of ammonia in the pre-neutralizer, remaining amount of ammonia is added in the granulator so that you will get the N by P ratio 1, N by P ratio 1, N by P ratio 1, so that we'll get the diammonium phosphate. We'll get the diammonium phosphate. So in this granulator, this slurry is converted into small granules. In this granulator, the slurry after the pre-neutralizer is converted to small granules in the granulator. It is, I already explained in the urea production process, to produce the granulars, what did we use to produce the urea granules? What did we use? Anyone remember? In the urea production process, to produce urea granules, we use one unit operation. Anyone remember what is that unit operation? Some tower I used. I give father some tower. I think it is a time to conduct a quick test. I think I'll announce, I'll message you about test so that you all will little spend some time to read it. So we use spilling tower. We used spilling tower in the urea production process to produce urea granules. Instead of that, here we're using the rotary granulator. Rotary granulator. So what is this rotary granulator looks like? Like here, we have an inclined drum. We have an inclined drum. And this is a perforated, like small holes. This is a perforated drum. This is the perforated drum. The perforations are made such a way that it will be like a nodule shaped. The perforations are made such a way that will be like a nodule shaped. So the slurry is flow over this drum. The slurry is flow over this drum, and through these nodules, the droplets or the particles, the slurry particles, thick slurry particles are dropped down. The slick slurry particles are dropped down. This ammonia vapor will be flowing through these granules. That way, this gas helps to form individual granules. This gases form individual granules. So this is hot. In the pre-neutralizer, the heat liberated. You can see here, this is exothermic reaction. So this is the hot solution is passing through these perforations, and small droplets, the small droplets of slurry is falling down. And here we introduce the cold ammonia. Because of that heat transfer. Some solidification of this slurry happens. The solidification. This is the drum. The droplets are falling. The droplets are falling. The slurry droplets are falling. This is very hot. Not a high temperature. Hot. Not very hot. Just say hot. The hot slurry is coming, and here we are blowing through the nitrogen gas through this one. So simultaneous heat transfer taking place from the hot slurry droplet to the cold ammonia. So that way it's getting solidified, and this ammonia also reacting with the whatever material is present here, and to produce monoammonium phosphate into diammonium phosphate. So some of the ammonia gases may not completely utilize. So those gases, unutilized ammonia gases, is taken back and again introduced into pre-neutralizer. The ammonia gas taken back and introduce a pre-neutralizer. If at all any particles comes along with this ammonia gas, they will scrub it. They will remove it with the help of the scrubber. They will remove with the help of the scrubber. So here ammonia introduced, droplets of slurry solution just fall down in the granulator, and the droplets are hot because there is exothermic reaction. Pre-neutralization is exothermic reaction. So those hot slurry droplets comes in contact with ammonia gas. Heat transfer takes place from the slurry particles. That way, the solidification of the slurry particles takes place. While the solidification is happening, ammonia also reacts with those slurry particles and converts to DAP. So that we will get the granules, solid particles, wet solid particles. And here we have the whatever unutilized ammonia is sent back to the pre-neutralizer. If at all any particles, because there could be fine particles uh, of diammonium phosphate or monoammonium phosphate may come with ammonia gas, so they will scrub it. They will scrub it. So this wet particles are introduced into dryer. The wet particles are introduced into dryer. So the dryer is also, I think I wanted to say, we also talk about drying here. So this is called rotary dryer. This is also called as kiln. Rotary dryer is also called as kiln. So how do you dry? How do you dry? So this drum, this is a drum, cylindrical drum. This is called rotary dryer. Sometimes also called as kiln. KILN. So this drum which rotates, which is rotated continuously, and particles are introduced. The particles are introduced. It'll have a baffles. If you see the side view, it'll have a baffles like this. You'll have a baffles like this. So what is the use of baffles? You know, when you introduce particles here, let's say the particles have fell down and stays in this baffle, stays in this baffle. When you rotate it, when you rotate it, what will happen when the particles are, when the baffle is such that, when the baffle is such that, you know, this is the baffle and particles are coming, the particles are carried down, and when the particles come to this stage, what will happen? By the gravity they'll fell down. By the gravity they will fell down. By the gravity they fell down. So this is the natural mixing. That is the natural way of mixing the particles. So particles taken and fall down. I'm sure you all have seen this concrete sand mixers in a construction. Concrete sand mixers in the construction, right? You will see a drum like this, drum like this. You know, they will have a baffles if at all observe inside. This sand part, as it rotates, the sand particles and concrete is get mixed. The sand particle current is mixed. Similar mechanism is used here. You will have a small kind of baffles, so that these baffles carry particles as it rotate and fell down. Is fell down. I'm sure you would have seen the ball mill animation shown by Manojit, uh, uh, Professor Manojit in the last semester, where the particles carry and fell down. Unfortunately, you're not able to see the physical lab, but if you see the physical lab, all these things should be easy to understand. Uh, so this, as the drum rotates, the particles goes up and fell down. That way, the mixing of particles takes place. So these are all wet particles. From the other side, from the other side, they will introduce hot air. They will introduce hot air. They will introduce hot air. So this hot air is blown from the other side, wet particles from the top, wet particles from the coming from the bottom. So the particles are surrounded with, the wet particles are surrounded with the hot air. the hot air. So this way, the heat transfer between wet particles and the hot air takes place. And whatever solvent is present in the wet particles, whatever solvent is present in the wet particles are dried up using the typical drying phenomena. So this is the dryer, typical rotary dryer utilization or rotary dryer function. So this is the rotary dryer or kiln. So here, so that drying, this drying, what after the granulation, whatever solid particles are formed, that will be sent to this dryer, where this wet particles are dried with help of the air. If they don't want to use the air, they will heat this drum externally, then they will circulate. They will heat the drum externally, either by electric or other means. They heat the drum externally, then they dry it. Now here you can see a screening system is used. Here a screening system is used. So three things can happen during the drying process. One thing can happen is during drying, as explained, the particles are, this is the drum, and when the drum rotates, the particles tend to fall down from the top to bottom. For the mixing point of view, we have to arrange that. But unfortunately, during mixing, because we are heating with help of air, unless you mix it, uniform heating will not take place, uniform drying will not take place. But as the particles are continuously falling, going up, fall down, going up, fall down, there is some attrition between particles takes place, heating between the particles takes place. So you will have very fine particles will be there. Those fine particles go along with the air. They go along with the air. So if you have very fine particles and air, gas and solid, and what unit operation you use, we can use a cyclone separator. So a cyclone separator used, and they collect all the fine particles, and air is sent back. Air is air is sent back. Now here, even though we have the coarse particles, but we have multiple sizes of the particles will be there. We will have multiple sizes of the particles will be there. Some of them could be very big, and some of them could be small, and some of them could be required size. So three types of solids will be coming out from the dryer: coarse size, coarse size, required size R, and we have the smaller size. After during the drying process, attrition of the particles will takes place. So three types of particles can form: coarse particles, that is big particles; required size particles; then we have the small particles. So we wanted to send, whenever you sell a product, we have to sell as uniform size particles. We cannot sell random size. Then the quality of the or the grade of that product will be reduced. So this required size particles will be separated from the coarse and small particles are separated, and the required size particles will be sent as a product. So all the three types of particles, we need to separate them. So we have a screen. We have screen, that is the required size. Whatever is oversized, that will be coarse. Whatever is oversized between these screens, there are two screens are placed. Two screens are placed. Whatever particles left over on the screen, that will be coarse particle. Whatever particles which come out passes through the bottom screen, that is the small size. And whatever is stays between these two sieves or meshes, that will be the required size. So two screens are there. Whatever is remain in between, that is the required, that goes to the next process. And whatever is overflowing, that is the coarse, and that is go to the crusher and goes to the goes back to the conveying system. Whatever is smaller size, that also collect in the conveying system. So fine particles, the fine particles, right? The big particles are crushed and made it fine, and small particles all are comes here. All are comes here. So these are all already DAP particles only. Whatever is collecting this the belt conveyor, this is only diammonium phosphate fertilizer only. But this that is not the required size. So all the particles are again, see all the particles all the way, all the way, all the way introduced into this granulator again, because where the wet liquids are coming. You have to make it wet to produce the required size. So again introduced into this granulator. Again introduced into this granulator. So thus the particles are further cooled down and sent to the storage for the supply as a diammonium phosphate. So simple process: pre-neutralizer, granulator, and dryer, and sieving screening system. These are the 4 unit operations. 3 unit operations and reaction is used in this diammonium phosphate. Diammonium phosphate pre-neutralizer, simple CSTR, then granulator, mechanical unit operation, dryer, another unit operation, cyclone separation, and screening. These are the 4 unit operations used in this diammonium phosphate. Very simple flow sheet. Even if you go to industry, that is very simple industry. Doesn't take very difficult thing to manage. If you see urea, if you see this diammonium phosphate, the complexity of process very less. That's why the uh, whatever skill level is less, and the process engine is limited, but they play a crucial role in this, because although it looks very simple, but if you don't maintain any grade, everything grade, then you will get random. You will not get required grade. The total skill comes here not in the process, but in the accurate way how we introduce these raw materials to get this required grade. That is where the major skill power is used. So that's all about fertilizers and important chemicals. With that, I finish all the fertilizers and important chemicals. Now I'll go to this, the last important chemical that we can generate from the solution, the chloralkali process. So it's already 9:56. I think I should not start this process. So I will talk about this in the next class, next Monday. So we'll continue next class this chloralkali process. That is one important chemical we use in industries, NaOH. This is very important base chemical. So far we talk about acids, but one of the popular base is NaOH. So if I explain this, that covers fine chemicals, that is grossly produces chemicals, and so I have selected fertilizers in this so that I can cover all the unit operations and types of reactors, various phenomena. So students, if you have any questions, I'm happy to answer here.
Hello.
Yes, Jagdish. One second, I'll just put my earphones. Yeah, please tell me if you have any questions. Jagdish, do you ask me any question to me? Please, if you have any questions, please ask me. Okay, maybe by mistake.